An important part of the Sibyl project was contributed by the case studies, where the project partners conducted in situ measurements and collected data about the existing buildings for their seismic evaluation. There were 3 case studies: Thessaloniki, Greece; Cologne, Germany; and L'Aquila, Italy. The measurement campaign in Thessaloniki took place in September-October 2015. 2 buildings of the Aristotle University of Thessaloniki were investigated: the administration building and the building of the Faculty of Philosophy. The building of the Faculty of Philosophy was designed and constructed in the 1960s. In the current state, it is a 5-story building consisting of 3 structural units divided by 2 separation zones. The bearing structural system of the building is represented by reinforced concrete frames and an elevator shaft located in the center of the building. The administration building was also designed and constructed in the 60s of the past century. It is an 8-story building. The lateral load resisting system comprises reinforced concrete frames and an elevator shaft. The shaft is located eccentrically in the floor plan, and therefore it may cause torsional effects in the building performance under seismic vibration. It is important to note that both buildings were designed in accordance with the old National Code of Greece, where on the one hand the estimated seismic hazard for the site was much lower in comparison with the current code, and on the other hand the ductility requirements were ignored. The measurements in Cologne were conducted in November-December 2015. With the support of the municipality of Cologne, we established direct contacts with 7 schools of the city. The administration of the schools showed understanding of the problem and interest in the cooperation. For some of the schools, the structural drawings of the buildings were provided by the school administration. However, for most of the buildings, no construction documentation was available. Therefore, the necessary information was collected on site. The schools are located in different parts of the city. The investigated buildings are of different size, different year of construction, and different structural types. There are in particular reinforced concrete frame buildings, buildings with masonry shear walls, and buildings of dual structural system. For all the schools, the program of investigations included ambient vibration measurements, both outside and inside the buildings, as well as visual structural survey and in situ inspection. The measurements in L'Aquila were implemented in May-June 2016. The building under study was seriously damaged during the notorious earthquake of 2009. Since that time, the damaged building is closed by the local civil protection authorities. The Sibyl team had no preliminary information about the building. No construction drawings were available. Therefore, this was a typical situation when the information necessary for structural modeling and seismic evaluation of the building was collected immediately on site within limited time frames. In this case, it took about 2 hours. The program of investigations also included ambient vibration measurements as well as visual structural survey and in situ inspection. The in situ investigations showed that the bearing reinforced concrete frames sustained the ground motions during the earthquake of 2009 quite well. They seem to be in a good condition and can serve their function, while the infill walls, which are made of fragile hollow bricks, were severely damaged or even destroyed. More details about the findings and results of the case studies can be found on the website of the Sibyl project. Now we can pay some more attention to the case study in Thessaloniki and consider in more detail the example of the building of the Faculty of Philosophy. As mentioned before, the measurements in Thessaloniki were conducted in September-October 2015, jointly by the groups of the Aristotle University, GFZ Potsdam and TU Berlin. The activities included visual survey and inspection of the structures, as well as short-term ambient vibration measurements. During the in-situ investigations for the geometry measurements, including both overall dimension of the building and member sizes, we used conventional measure tapes and a laser distance meter. For scanning concrete members to detect the location of reinforcement bars and determine the depth of concrete cover, we use the multi-detector Hilti PS50. The vibration measurements were performed using geophones connected to data loggers, which were placed in selected parts of the building, and their location was carefully documented. The construction documentation provided by the partners from the Aristotle University included some architectural drawings and limited specifications containing information about the building and its parts. However, the available documentation was not complete. In particular, information about some structural details and properties of materials was not available. And moreover, as it was found out in the course of the in-situ investigations, a considerable part of the preliminary available information was incorrect. In particular, one additional floor was detected on site in comparison with the original design drawings. It was found out later that the building was modified 20 years after the construction. However, there is no related documentation. Moreover, some considerable discrepancies, in particular in cross-sectional dimensions of structural elements in comparison with the original drawings, were detected during the conducted in-situ measurements. These findings emphasize the importance of in-situ inspections for assessment of existing buildings. Structural modeling and analysis solely based on the original design drawings may produce misleading results and therefore inadequate decisions. Even limited inspection and short-term monitoring of the state of existing buildings can considerably contribute to the quality of structural models and improve the results of vulnerability analysis. For the simplified structural analysis, we focus on the central part of the building. For modeling the building, we take into consideration that the structural system is represented by moment-resisting frames composed of reinforced concrete columns and beams. The lateral load-resisting system is complemented with the reinforced concrete elevator shaft located in the center of the building. On the upper floors, there is also a system of masonry walls defining the internal functional arrangement of the building. The walls do not belong to the support framework, however they contribute to the stiffness and mass of the structure. Therefore, they have also been included to the structural model. The structural system is completed with reinforced concrete floor slabs, providing the spatial integrity of the building as a whole. The modeled system is considered fixed at the ground level, and for the sake of simplification, we do not take into account possible influence of the underground part of the building, and neglect possible ground structure interaction effects. This scheme shows the spatial arrangement of the system of installed sensors for the operational model analysis. The measurements were concentrated on the central part of the building, which was monitored with sensors placed at the four corners of the first, second, third, and the fourth floors. As well, two sensors were installed on the roof and two in the basement. The two side units of the building were also monitored, but less densely. The sensors were installed at the four corners of the first and the fourth floors, and one sensor in the semi-basement. The model analysis was implemented with the help of the MACHEC software, using stochastic subspace identification approach. Several 3-minute long recordings selected in the different periods of day and night were analyzed and compared. The calculations for all the analyzed recordings gave very similar output. Here you can see the 3 vibration modes obtained from the operational model analysis. The obtained fundamental frequencies for the 2 bending modes are equal to 1.6 Hz in the lateral direction and 1.72 Hz in the longitudinal direction. The frequency corresponding to the torsional mode is 1.76 Hz. From consideration of the obtained results, we can see that the separation joints are only in part efficient, because there is still some coupling between the central part and the side parts of the building. In the further analysis, however, we focus on the central part only and neglect the influence of the side units. In terms of the Eurocode 8, the amount and quality of available and collected information for the building corresponds to the limited knowledge. This level reflects, in our opinion, the most plausible situations in the routine practice of civil protection. The lacking information necessary for the structural modeling, in particular structural details and material properties, was updated using simulated design. That is, the required input parameters for the model were taken according to the usual design practice for such buildings. For building assessment corresponding to this knowledge level, we developed a simplified approach based on so-called simplified integral structural model. We have produced another video describing the methodological aspects, which is also located on the website of the Sibyl project. There you can find more details about the developed approach. Here you can see the interface of the Excel-based tool. When the user completes the data input, the calculations start automatically. As a first iteration for the model based on the collected input data, the vibrational modes and frequencies are numerically computed and compared with the measured data to check the quality of the model. And in case of notable discrepancies, the parameters of the model should be corrected, tuned correspondingly. The refinement of the model should be done using those building characteristics which are associated with largest uncertainties in the available input data. In particular, they may be related to unknown cross-section sizes or mechanical properties of the structural members. Comparing the bearing capacity of the structure with the level of earthquake load for the site, with the use of this tool, we can estimate the expected level of damage. 3 possible limit states of reinforced concrete structures are considered. Limit state 1, first cracking in the concrete. Limit state 2, first yielding in the reinforcement. And limit state 3, failure of the structure. The numerical results obtained for the building under consideration show that at the given level of seismic loading, one may expect occurrence of the limit state 3 at the level of the ground floor, while the upper floors perform much better. In particular, the results obtained for the X direction show that only the limit state 1 is achieved in all the upper floors, while for the Y direction, the limit state 2 is achieved on the 2nd and 3rd floors, and the limit state 1 on the 4th and the 5th floors of the building. Considering the obtained results, we may conclude that the presence of the weak ground floor makes the building seismically vulnerable. Therefore, strengthening of the bearing structural elements would be recommended. At the same time, we should keep in mind that in our simplified assessment, only the central part of the building was considered, neglecting possible influence of the side units of the building. Furthermore, we have to take into account considerable uncertainties in the input parameters, inasmuch as we had to use simulated design due to the lack of reliable information about the actual parameters of the building. Nevertheless, our estimation obtained with the simplified approach reflects the in-situ findings. In particular, the presence of soft story and the predicted damage mechanism in case of a strong earthquake seem to be plausible. For more details regarding the developed simplified approach, please contact the Department of Structural Mechanics of TU Berlin. Regarding the outcomes of the Sibyl project, you can find more information on the website of the project. We highly appreciate the financial support of the European Commission.